Now, device-independent entanglement certification is a nice way that this can be done in a hardware-agnostic manner, and it's really important that these methods can be hardware-agnostic because there's many different platforms on which a quantum network can be implemented. So our approach to certifying those resources can be uniform across all those platforms. So in this approach, a referee certifies whether devices A and B are entangled in a way that is totally agnostic of the device's hardware and the device's software. So here we simply need to demonstrate a loophole-free violation of the CH-SH inequality, so we just follow the standard protocol. The referee will draw inputs X and Y uniformly at random and send them to the two devices. Then the devices will measure their local entanglement and send it back to the referee. And then the referee will check that the measurement results are coincident and that no signaling occurred. To ensure that no signaling occurred, the referee needs to know the positions of the two devices and to make sure that their distance between them is not short enough to allow communication within the duration of the test. And to do this, the referee could apply quantum position verification to establish each device's location. However, we'll save discussion on quantum position verification for another webinar. A protocol that can be built off of device-independent entanglement distribution or certification is device-independent quantum key distribution. Here, the goal is for two network users, Alice and Bob, to establish a secret key using trusted black box devices and an entanglement produced by an untrusted network. So Alice and Bob don't really know if they're connected with a entanglement source, or that entanglement source might not be very good quality. Now, the security of their protocol will depend on the quality of that entanglement source, and they want to, ensure that they are using secure quantum resources. So to do this, Alice and Bob perform a variation of a bell test. So Alice will draw a value 0 or 1, while Bob draws a value 0, 1, or 2 at random. They give each of these values to their devices, which the values 0 and 1 are used to perform CH-SH measurements, where we note that when Alice has 0 and Bob has 2, that they will measure in the same bases. So after Alice and Bob have recorded their measurement results, they'll communicate over a public classical channel and share what their drawn values were, what inputs they gave to their devices. Then anytime that Alice and Bob each input the values 0 or 1 into their device, they use that data that they recorded to verify that the CH-SH inequality was violated. Meanwhile, a secret key is established in all of the cases where Alice said they measured 0 and Bob measured 2. Remember, in this case, they measure in the exact same basis, so if they share entanglement, then those values will be the same. Note that if they do not have entanglement, then the maximum value of the CH-SH inequality cannot be attained, indicating that their secret key might not be secure or shared between the two parties. So baked into this protocol is both a certification and key distribution aspect to ensure that keys are only distributed using secure entanglement resources or ideal entanglement.